In finding all values of t such that this determinant equals 0, we can say that the determinant is a real number, useful because it has applications in calculating area and volume, and using the determinant to reveal if a matrix is invertible by using the entries of a square matrix, we can see if there's a solution to the system of equations. And yeah, of course, area and volume, those are cool, but in my experience, one of the more interesting applications is in cryptography. And sending secure signals or messages sent encoded inside of the matrix is pretty cool. And since data can only be decrypted with an invertible matrix and its determinant, we can focus on the determinant as an indication of the invertibility of the matrix, and calculating the determinant of a matrix involves this, very simple breakdown of 2 by 2 matrices. Now, for larger matrices, this becomes pretty inefficient, and using something like matrix decomposition or matrix factorization would probably be a better bet. And just looking in retrospect now, we can actually even think about this as with Kramer's rule as well. So this is pretty interesting. This is Kramer's rule is a method for solving a system of equations using the determinant. And since it gives us the unique solution to a system of equations, if it exists, if we can find this solution, then we have effectively broken the cryptography, the encryption, or solved it, or just decoded it using a valid key as intended. But if the system has no solution or infinite many solutions, this can be indicated by determinant of 0. And to find if the system is inconsistent or dependent, you have to use elimination. This is not indicative of that. Um, and so we're not going to use Kramer's rule here, but we can think about the application of it and the implications of it. And so what we're going to do now is actually called cofactor expansion, sometimes called Laplace expansion. And the way that we do that is to break this 3 by 3 down into a 2 by 2, since 2 by 2s are a lot easier to work with. And as you can see, as you start getting a lot more complicated and a higher order of matrices, this will become quickly inefficient to do, and we can move on to things like Kramer's rule. And that's why I mentioned it in the beginning, because even matrix factorization is a lot more efficient than doing something like this. This will take a lot of time and processing power, and it's highly inefficient and can be confusing to do by hand. But the 3 by 3 is a perfect example of how to break this down. And how we're going to do it is we're just going to start breaking things down like this. T minus 1, we're going to pull out from this, and we're going to start making these little matrices like this. And so we can think about this as now the determinant of t plus 2 and 0, like I said, we're going to just take this little block and make its own little matrix, t plus 1. And this is the determinant, so we have to take the determinant of this as well. So then we're going to move on to the next. And it's going to be 0. We're going to use this as our anchor, and we're going to ignore the rest of this. And obviously this column also, and row. And so we're going to do 0, and we're going to just take what's in here, not counting the row that we've already excluded. And so this is going to end up being -2, -1, 0, t plus 1, right? And then and this can be, you usually have to follow something like this, but since it's a 0 right here, that's okay. And so we're going to say plus 1. So now we're shifting the matrix even further, and we're taking this as the anchor, and we're going to start taking this as the determinant matrix that we have to find. And this is going to be -2, t plus 2, and then this is going to be 0 and 0. And there we go. That's how we set this thing up. And in the next steps, we'll see how we actually can solve using the determinant. And so oop, this implies that taking the determinant, you have t minus 1 times t plus 2 times t plus 1 plus 0 plus 1 times 0, and this gives us 0. And that's how we set this up. And so solving like this, we can even break this down now further. T minus 1, and this implies t minus 1, t plus 2, t plus 1 are equal to 0. And now solving for t gives me t minus 1 equals 0, t plus 2 equals 0, and we want to find all values, remember, so that's why we have to set all of these different t's equal to 0. We can get t equals 1, t equals negative 2, and t equals negative 1. And now we have found all t that satiates and makes this equation true. And those can be found right here. So, as you can see, we've solved for all t that satiates this equation, and we'll see you in the next video.